Hello, everyone.
Yes, I
Um,
can hear you.
can you hear me?
Yes.
Okay, so hello, and first of all, I would like to thank the organizers for giving me the opportunity to speak here at the JpGU. And today I will be presenting our results on propagating waves inside the quiescent solar prominence using a kind of 3D wavelet approach. So first, I would like to remind you what are solar prominences. So those are cool, dense, and complex plasma structures sustained by the intricate topology of coronal magnetic field. And they are chromospheric in nature, but can be observed in both chromosphere and the hot tenuous corona as well. And what is important that the structures often become unstable, eventually erupting as coronal mass ejections. And for almost 2 decades, that there was a different classification of the solar prominences. However, I will focus on the classification based on their evolution. So the quiescent prominences are relatively cool magnetized materials, relatively low suspended in the solar corona above the solar surface, and these are non-eruptive ones. In contrast to the eruptive prominences, which are characterized by rapid upward plasma acceleration from velocities up to even 1000 kilometers per second, and those eruptive ones develop into CMEs. And we have also the last one. These are coronal clouds, but these are very calm, very high suspended material in the corona, up to 200,000 kilometers. And they have V-shaped, and they called sometimes coronal spiders. But we will be talking about quiescent prominence, and we are very fortunate because thanks to the space-borne telescopes such as Stereo Ahead or Solar Orbiter, we can observe solar prominences from multiple angles. And this plot shows the spacecraft positions. One is stereo, two is Earth, and three is solar orbiter. So the inclination angle of solar orbiter is about 170 degrees relative to the Earth, giving us the far side view of the prominence. And unlike the stereo, which you can see has an inclination only of about 18 degrees and showing the near side view of the same structure. So we also can observe this prominence with the Solar Dynamics Observatory and the AAA instrument in the 304. So the combination of the data coming from these three instruments provides vertical cuts through the structure. So you can see like we have three vertical cuts through the same prominence from the different angles. And also the 304 channel corresponds to the slightly singly ionized helium, which forms at around 50,000 kelvins. So this means it mostly captures the emission from the transition region and the lower solar corona actually. And 304 line is optically thick in prominences, so this means that radiation doesn't penetrate deeply. So most of the helium-2 emission comes from the outer layers, while deeper regions remain like kind of hidden. And what is important that this prominence was investigated by Professor Ichimoto in 2024, and his team was using Japanese ground-based telescope SMART and the SDDI instrument, and they were measuring this prominence in two wavelengths: chromospheric H alpha, helium-1 1083, I guess, and it was H alpha line is optically thick in prominences and probes much cooler chromospheric plasma. So while near infrared helium-1 1083 line is typically optically thin. So this allows to probe the most inner layers of the prominence. So actually these plots here are showing Fourier and wavelet analysis of the target prominence. And Ichimoto found, using a helium 1 slit measurement, dominant periods of about 910 and 240 seconds dominant periods. And these results were also overplotted on the wavelet here. I don't know whether you see my mouse, but these results were very interesting to us. However, the wavelet analysis was only limited to a small field of view, marked here by the intensity image with the white slit. So therefore, we wanted to investigate, broader our investigation, and using wavelet analysis for the whole field of view of this measurement to basically localize the dominant period. And what is important, we also included spaceborne observations to check for possible correlations between the chromospheric and coronal layers of the prominence. So all instruments observed in the same time, and in the same wavelength, helium 2304, but each data set had different temporal cadence, and as we can see later, it was quite important. So we calculated the 3D wavelet, but first we used 1D approach slit wavelet and found that some signals laid outside the wavelet's influence cone. So basically, as you can see, the wavelet power spectra for SDDI and AI 304, as well as stereo, can be considered as the results that you can basically rely on, because the found periods lay inside the influence cone. However, when we checked the solar orbiter data, then we saw that actually here the results are lying outside the influence cone. So meaning they could not be considered as a significant. So unfortunately, we had to eliminate this solar orbiter data sets. So here you can see how it was done. And we also calculated 3D wavelet for the H alpha data sets from the global power spectrum. So from this kind of pyramid, we found that actually there are 3 dominant oscillation periods, and represented here by 3 different colors. So blue indicates 3 to 6 minute periods, green corresponds to 14 to 17 minutes, and red shows 28 to 31 minutes. And this kind of colorful black cocoa plot is like kind of superposition of these 3. However, when comparing this with the 1D wavelet, we found that it becomes clear that the oscillations within 3 to 6 minutes periods cannot be considered significant as periodic waves. They might be excited by the external drivers, as shown in the blue plot, but these oscillations are mostly present near the solar surface. So we calculated these 3D cubes representing the temporal and spatial distribution of each frequency band for both ground-based and space-based data sets. So you can see on the left side we have cubes for the SSDI Dopplergram in H alpha. On the right side there is a stereo A intensity in the 304. And now I will show you the video where you can see how the 15 minutes oscillations propagate through the prominence over time. And on the left is a context image of the intensity data from SDDI. And on the right, there is a 3D wavelet results for the 15 minutes oscillation. So you can see there is a change within a time. They are kind of filling this loop at some point. So to investigate that more, we kind of selected central parts of the prominence using loops and slits to investigate horizontal plasma displacement and inflows within the prominence structures. And as you can see, we found inflows of the velocities of even 1100 meters per second. And the horizontal flows were smaller. There were only like 300 meters per second. Yeah. Okay, and summarizing, based on the wavelet power spectra, we found that the oscillations in a prominence body with a period of 3 to 6 minutes. However, these oscillations must be neglected as a result is not statistically significant. Then significant periods for the cool plasma measured by H alpha line as following 14 to 70 minutes, and then there is another period with 22 to 41 minutes. Next conclusion is that the 3D wavelet analysis confirmed that the 15 minutes oscillations propagate inside the prominence body, and in this case, inside the prominence body is dominated by the intermediate period oscillations. Next, the coronal plasma and the outer part of the prominence is dominated by the long period oscillations, peaking at 49 to 53 minutes. So there is a difference between the inner and outer part of the structure. So the time distance diagrams revealed that the plasma velocities inside the prominence body with the inflows of 600 up to 1100 meters per second, and the horizontal motion is approximately 300 meters per second. So I don't know why it... Oh, okay. So basically that was all. Thank you. I don't know why my last slide doesn't work, but...
Yes, thank you. So I'll take questions. Yes, please.
Thank you for a very interesting talk. My question is, why are you ignoring the periods of 3 to 6 minutes? What is the physical reasons for it?
Yeah, on the wavelet spectra, because previously we thought that this result is actually like a real result, but in the wavelet spectra we saw that there is no consistency over the time series, so they are kind of peaking, showing up, and then disappearing. So this kind of behavior, kind of forced us to check it with the significance levels for the whole time series, and actually they are lying outside the statistical significant level. So they are not, they cannot be confirmed actually as this probable result, which is very sad, I would say, because we thought that they might be some inflow from the photosphere or even from the chromosphere, and there is, but those might be driven by some outer external forces or some phenomena. But these are not like kind of consistent through the whole time series.
Thank you.
Okay, thank you very much. And if there's no more question, let's thank the speaker again.
Mm-hmm. Thank you.
So our last speaker in this session is Dr.